Okay, let's go ahead and get started. I made another version of the personality output file. We're over 200 now, and still pretty high percentage of introverts. I think this one is a little over 69% introverts. I'll give you one last chance, so you can still go to this link and fill it out. I will post a final version on Friday and say a few words, kind of to put homework 7 to rest then. Let's take a look at our question for the day last time. This was a fun question about what people pay attention to. I was glad to see that 3/4 of you pay attention to me. I often am gesticulating in various ways. I'm glad someone is noticing that I do some strange things like that. So let me say a little bit. So you got email from me on Friday letting you know that I was extending the absolute cutoff for number 6 to Saturday night, and I gave you an 11th free late day, so everybody has 11 free late days. Homework 7 was due last night. I'm not going to extend it or give you an extra late day, but I'm extending the cutoff. So normally it would cut off on Friday. I'm giving you again until Saturday for the cutoff. So I'm changing the cutoff to Saturday instead of Friday for homework 7. So you have a little more time, and you have those 11 free late days that you could apply if you need to. For the new homework assignment that I'm distributing today, I'm going to make it due on Wednesday of next week, and it has a slightly longer period. It has until the Sunday, for a cutoff for it. This assignment involves Chapter 8. We've been talking about objects and classes, and I've mentioned that this is a very different way of approaching things. It's a very different understanding about things to work with objects. So I expect that you're probably finding it a little bit odd, probably somewhat confusing. There, I guess, are different philosophies of what you could do as a last assignment. One way to go would be to kind of give you a little bit of exposure to writing a class, something very simple. I guess, I think of it as an analogy that if you think about people who've only lived on the land, they've never seen water in any quantity, and so you've never seen a lake or an ocean or a river or anything like that. So how would you get someone like that used to this other way of existing? Well, you could have a little kiddie pool and have them splash around in the kiddie pool a little bit, and they get a little bit of an idea about what water is like. I don't think that's the right way to go. What we do is we kind of throw you in the ocean. So this is very different, what you're going to experience. We're going to kind of give you this experience of what it's like to be incredible number of objects, not just 1 or 2 or 3, but tons of objects floating around. So it's a very different kind of assignment. And to make this assignment work, what I've done is I've written a whole lot of supporting code to create a kind of programming environment that you can program within. Well, let me just go ahead and show you. I have put this up on the class webpage, homework 8. I opened it though before lecture. There's going to be this world in which critters are wandering around, and I've written a whole bunch of code that supports the critter simulation that we call it. You are going to write some classes that are going to be fit into my framework. So you're writing a little bit of code. I wrote tons of code, that kind of makes this whole thing work. So a very different kind of experience. This kind of assignment is something, when intro instructors first switched to teaching objects, we found that we often needed to write assignments this way. Because the thing is, we've been having you write up to 100 lines of code, to practice things like parameters, while loops, for loops, and so forth, arrays. You can write 100-line programs that use arrays in an interesting way. You can't really write 100-line programs that use classes in an interesting way. You just need a much bigger code base in order to make classes interesting. So these object kind of assignments tend to have a different character to them because they have all the supporting code that goes along with it, something instructors call scaffolding. So there's a lot of scaffolding support that makes this thing work. And I kind of tell a joke. But it's at least halfway serious that with an assignment like personality test, I feel like you spend maybe an hour reading the assignment write-up to understand it. What are these different dimensions of personality? What is the order of these A and B answers? So it takes a while to read through the assignment write-up and understand the details. And then you spend 4 or 5 hours writing the actual code, because the code is complicated. And with these kinds of assignments, I find that what students do is they spend 4 or 5 hours reading the assignment write-up just to understand what it is they're supposed to do. But then when they go to write the code, they find that there's not that much actually to do. So it's maybe an hour of coding. I mean, it's an exaggeration, but it kind of gives you the idea that this is going to feel like a different assignment. It's going to be one where you're going to have to read this assignment write-up probably multiple times in order to understand it. There is a lot here. There's a lot of detail to understand in order to understand what to do. But in the end, I'm not asking you to write a huge amount of code. So this is different than homework 6 and 7. I said 7 was going to be the most complex in terms of lines of code, and the amount of coding that you had to do. This is hard in a different way. This is hard in that you need to understand this simulator world in which these critters are defined. If you print your homework assignments, and I recommend that you do, I would say pause this right now and print this assignment write-up right now so you'll have it for what I'm going to do in the next 45 minutes so that you can kind of follow along. I'm going to refer to the assignment write-up often. I mean, if you can't print it, it's not that big a deal, but it might be a little nicer if you were going to print it anyway to go ahead and print it early. So as I said, this is an assignment that involves this kind of critter simulator, and we'll take a look at that in a second. Well, actually, let me just go there. You'll find that there's tons of classes involved. So you're going to have to download a lot of different classes. I have a zip file that you can download that has all the different classes that you'll need, a whole bunch of different supporting classes. There's only one that has a main in it, and I called it critter main. So there's a file called critter main. This is what it looks like, the version that you'll download from the course web page. So there's an object known as a critter frame that we end up talking to, and we give it commands like here it's saying, hey critter frame, please add 30 flytrap critters to the simulator. Hey critter frame, please add 30 food critters to the frame. And hey frame, why don't you start the simulation? So these are the kinds of commands we give. These are commented out because we're not ready to give those commands yet. But so you'll be working with this critter main and commenting out things, putting things back in, doing different combinations of critters to run with the simulator. Let me just show you what happens if I compile and run this version of it, kind of the as-is version that you get when you download it. It is letting you know that there are 30 flytrap critters and 30 food critters in the world, which is what we expected to be true. And then there's a bunch of different controls here. I'm going to just say start the simulator and let it go. And so as we're moving along, actually, let me do this. I'm going to try this one more time. I'm going to try running it once more. I want to see if I can get a certain thing to happen, and I'm going to tell it to start. Now, something happened here that you might not have noticed. It had the same 30 flytrap and 30 food initially, but a little something has happened where we've got 32 and 28 now. So I'll explain that as we go through this today. So this is a world that has 32 flytraps and 28 food. It's not very exciting. You can see the step counter is going up, so clearly, and I could speed it up if I want to go even faster, and you can see the step counter go up even faster. It's just that these are very dull critters, the flytrap and the food, in terms of they don't move, so that's why we're not seeing much going on. So let me go ahead and I'll end that execution. Let me go to the assignment write-up, and I want to show you some things that are on page 2 of the assignment write-up. So there it describes to you that what you're going to be doing, you're going to be defining 4 different critter classes. Well, we'll do it even one more. So you're going to be defining 4 different classes for 4 different critters that we want you to create, and for each of them, you're going to define 3 different methods. So you're going to have a toString method that indicates how it should be displayed, what text to use to display it. You're going to have a getColor method that returns a color that tells it what color it should be, and getMove. And getMove is the more complicated one of these different methods. I'm going to pass you, as a parameter, a critter info object. So I'm giving you an object that you can talk to. So think of it as one of your critters is given this kind of info object. It's like being able to connect to the web or something and look things up in Google or whatever. It's going to talk to that critter info object and ask it about the state of the world. Ask it about, what is true right now for that critter. So the critter info object gives you information about what's going on for that particular critter in the world. It gives you information about what's going on in the world. And it has to return an action. So there are 4 different actions, and they're listed here in the table. So critters are facing in a particular direction. North, south, east, and west. So they're facing some direction. And one of the actions they can take is to rotate to the left. So kind of rotate 90 degrees to the left, rotate 90 degrees to the right, are possibilities. They can hop forward, which lets them move in the world. The food and the flytrap were not doing hop, so they never used that option. But that's going to be something that most critters will do, is they'll tend to hop. And then there's this option called infect. So here's the idea. In this simulator, critters are never really born and they never really die. So we were running that simulation, and I've probably already ended it. We had the simulation where there were 30 fly traps and 30 food, so there were 60 critters. If you start with 60, you'll always have 60. So, critters stay alive forever. But what you can do is that if you notice that there's a critter in front of you of another species, then you can infect it with your DNA. And so if you do this infect move, there's a whole lot of terrible, Star Trek episodes and other science fiction episodes where, something gets converted into another species because, this new DNA takes over and converts it into a different kind of thing. So that's the idea that we're using here. And that's why, when I ran it a second time, and you saw that we ended up with 32 fly traps and 28 food. So 2 of the food got infected and turned into fly traps. So fly traps had kind of succeeded in converting 2 of those food objects into fly traps. So, and that means that the number of each critter in the world over time varies. And some critters do better and some critters do worse. So there's a kind of a competitive aspect to this. Who will survive? There'll be different strategies. And if you are successful at infecting other critters, then there'll be more of your kind of species. And so that's kind of a lot of what's going on here. I guess it's worth mentioning, but I'll obviously be saying more about this in the next few lectures, but we are going to have a critter tournament on the last day of class where we're going to encourage students in the class to submit their critters that they've come up with, and we'll have a contest to see which critters survive the most. So there'll be an overall contest for the class. We also choose critters that we consider to be entertaining. So there's also kind of a category that you can win in by having an entertaining critter. Okay, so that's, we're basically defining 3 methods for each class, and the getMove one is the more complicated one. There's kind of different rules for when you take different actions. So I want to go through 3 of the required classes. So I'm going to go to page 4 of the assignment write-up. This is page 4 of the assignment write-up. And this is one of the most useful parts of the assignment write-up. It mentions that you're to implement 4 classes: bear, lion, giant, and husky. Now, husky, you get to decide what those 3 methods do. So that's going to be the one where you come up with a critter. And as I said, we'll have a contest, for different huskies to see whose husky does the best in the class. But these are 3 kind of required critters where I tell you what the critter is supposed to do. So let's talk about each one. So there's a bear class that you're supposed to define. Now, it has a different kind of constructor than other classes. It has a constructor that takes a Boolean. So when you go to define the bear class, you're going to have to include a constructor that takes a Boolean, and that tells the class whether to be constructing a polar bear or not. So it's kind of true for polar bears and false if it's not supposed to be a polar bear. So, and then the way the getColor method works is that it returns either white or black, depending upon whether it was told to be a polar bear. There's a Tostring method that sometimes displays a slash and sometimes displays a backslash, and it says it should alternate on different turns, is what it should do. And then in terms of getMove, all of these things, I think, begin with always infect if an enemy is in front. That's just rational. The name of the game here is getting a lot of your species. So, infecting is kind of an obvious thing you want to do if there's an enemy in front of you, kind of a critter of another kind. So I think they all begin with this little description that you would infect if there was an enemy in front of you. And otherwise you would hop if possible. Well, when would it not be possible? Well, there might be a wall in front of you, in which case you wouldn't hop. Or there might be one of your kind of critter in front of you, in which case you don't want to hop. And otherwise you turn left. So that's kind of the description of what you do. I found that when I gave the assignment in this form, students kind of didn't have a good way of testing to know whether, they kind of understood what they were supposed to do, but they weren't sure whether their critters were behaving properly, whether they had implemented it properly. So I added something to the assignment write-up that I'm going to show you in a second. Let me mention one of the things that I like about this assignment is that I think it's a good example of what I would call emergent behavior. So I've described to you here the behavior of a single bear. And what I would say is that when you throw a bunch of these bears into this world, following the rules of this world, that you kind of get behaviors that emerge that weren't obvious from the way that you described the individual critter. So let me show you on page 6, so I'm switching to page 6, there are 3 paragraphs here at the end that describe the 3 different required critters, including the bear. So let me kind of have that one be sitting here. And what it says is, try running the simulator with just 30 bears in the world. So I'm going to comment out this, and I'm going to comment out this. I don't want any fly traps or food. I just want 30 bears. So I'm going to run it with 30 bears in the world. I've written a solution to bear, so I have a solution to this. I'm going to compile the main and run. And so we're kind of executing here. Now let me kind of try to have both of these up at the same time so that we can watch what's happening in the world while we read what's down here. Try running the simulator with just 30 bears in the world. You should see about half of them being white and about half being black. Well, if you take a look at that, it looks like it's about half of them are white and half of them are black. By the way, let me mention that one of the things that's confusing about the bear, well, and this is confusing in general for this homework, is that you're used to doing everything. We've had you write, a class where you wrote all the code. This is going to be very different here, where you do some things but not other things. You're not in control. You're in a world where the simulator is in control. So that's going to be a very different way of doing things. In terms of, there's going to be a kind of a flipping of the coin, a random selection of white or black. You do not do the random selection, the simulator does. So when the simulator goes to make these 30 bears, it decides whether to make them polar bears or not. So it passes a true or a false to the constructor for the bear class, and so it's the one that kind of is doing that randomization to get half of them to be black and half of them to be white. Initially, they should all be displayed with the slash character, which they are. When you click step, now before what I did is I hit the start button, which just started it running at a relatively slow pace. We saw a step counter here that was going up. But you have the ability to do the fine-grained step, 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 and when you're debugging or trying to understand how things are behaving, step is a more appropriate thing to do. So it says, should all be displayed as slash characters. When you click step, they should all switch to backslash. So I'm about to click step, watch what happens. That's stop, not step. Okay, we'll click step, and they all switch to backslash characters, which they did. When you click step again, they should go back to slash characters, step again, and step again, step again, step again. So slash between slash backslash. That's kind of the alternating to string that it's supposed to do. When you click start, you should observe the bears heading towards walls and hugging the walls in a counterclockwise direction. They'll sometimes bump into each other and go off in other directions, but their tendency should be to follow along the walls. So let's hit start and just watch it go. And so you can kind of see that behavior that was being described is they do head toward walls, and then they do kind of follow, hug the walls, going in a counterclockwise direction. Now this one ran into another bear, and that's why it kind of wandered off in another direction. But now it's back to wandering around, going in the counterclockwise direction with the wall. And we can speed it up if we want to kind of watch it run faster. And you can see the occasional bear that gets kind of, runs into another bear and it goes off in another direction, but eventually it comes back to the other group. So I guess what I would say is that some of what's being described here is emergent behavior. I didn't say in describing the bear's behavior that it should hug walls or that it should move counterclockwise. I didn't say any of that. That just kind of comes about naturally because of the individual behavior I defined and the nature of this world, where the walls are, kind of how the world is shaped and so forth. So that's an example of this idea of the emergent behavior. Okay, so that would be a way of seeing whether your bears are behaving properly. So let me go ahead, we can end that execution. And let's talk about the next one. So there's a lion class. The lion has a zero argument constructor, so it doesn't have a special constructor like bear. And it says that get color, the way that this should happen is that it should randomly pick one of three colors, color.red, color.green, color.blue, and it uses that color for 3 moves. Then randomly picks one of those colors again for the next 3 moves, then randomly picks another one of those colors for the next 3 moves, and so on. So it's kind of describing the behavior of the kind of the observed behavior of get color, is that based on different moves that are happening, that it should be having a particular color, one of these 3 choices, for 3 moves in a row. And then it should have a different color for 3 moves in a row, a different color for 3 moves in a row, and so forth. Now, this is going to make you think, I'll have a for loop that goes 3 times, and that's going to turn out to be the wrong thing. We use lots of analogies for this. One of the analogies people have is think about a game show. So if you are, on Wheel of Fortune, where you get to guess a letter, right? And then we kind of go to the different contestants. This would be like you deciding to make 3 guesses in a row. But you don't get to make 3 guesses in a row. You're participating in this game show where there are rules, and you have to wait for the host to ask you, what's your next guess? And that's a similar thing here, is that I'll ask you, what's your next move? And then later, what's your next move? And later, what's your next move? And as I'm doing that, as I'm asking you about what moves you want to make, I want you to be displaying yourself in one color for 3 of those moves, in another color for 3 of the moves, in another color for 3 of the moves, and so forth. The toString method always returns an L. Get move begins with that common behavior I mentioned. Always infect if an enemy is in front of you. Otherwise, if a wall is in front of you or to the right, then turn left. Otherwise, if a fellow lion is in front, then turn right. And otherwise, hop. So that's kind of the description. You could place your bet about what you think is going to be the emergent behavior. What is that going to mean in terms of what we would observe? And then back on page 6, there's a paragraph that describes what we should see with lions. Begins, try running the simulator with just 30 lions in the world. So let's take the bears out of it. Let's run it with 30 lions. So let me compile and run it with 30 lions in the world. And we'll bring this description available to us again. Try running the simulator with just 30 lions. You should see about 1/3 of them being red, and 1/3 being green, and 1/3 being blue. In this case, we did make the choice about whether it was red or green or blue. Use the step button to make sure that the colors alternate properly. They should keep these initial colors for 3 moves. That means that they should stay this color while the simulator is indicating that it is step 0. Right now it's step 0, and so we're seeing the colors for step 0, step 1, and step 2. So when this counter is showing 0 and 1 and 2, we should be seeing this color scheme. So let me do the step command. So we'll move to step 1, and we'll move to step 2. So 0, 1, and 2, you could see that they were the same color during those different times. They should switch colors when the simulator indicates that you are up to step 3, and should stay with these new colors for steps 4 and 5. So basically, we are expecting that the color scheme will change when I hit the step button again. So let's try to remember we had a blue and 3 greens. We'll kind of watch this. There's kind of a Murphy's Law of demos that this could be really unfortunate what could happen, because this lion might randomly choose to be blue again, and these 3 might randomly choose to be green again. It's unlikely, but it's possible that they could all choose to kind of be the same color they were before. But let's kind of see what happens when we do step. And so now we got, well, this one did stay blue, but these 2, and this one stayed green, but these 2 switched from green to blue. So it's a new color scheme that we have, and you could be looking at your other lions to see. That was when we see step 3 being displayed. So that when step 3 is displayed, we would see this, and then also for steps 4 and 5. So when we see step 4 and we see step 5, we've got that same color scheme. Then you should see a new color scheme for steps 6, 7, and 8. So I'm about to hit step. We could watch this little universe down here, green, blue, blue. We could watch what happens, and that's red, green, green. So we got a switch there, and that was for 6, 7, and 8. So it's kind of giving you a very detailed description of what we expect to see with these different colors, and with the step reading these different kinds of values. So very, very specific about the transition, when it should occur, and so forth, what you should be observing. When you click Start, you should see them bouncing off of walls. When they bump into a wall, they should turn around and head back in the direction they came. They will sometimes bump into each other as well. They shouldn't end up clustering together anywhere. So let me hit Start. And so and let's go ahead, we'll speed it up and kind of watch it a little bit. So they bounce off of walls back and forth, no clustering anywhere. They're not hugging walls, a very different kind of emergent behavior that we see for the lions. And they're changing colors. It's a little fast to try to see that as the steps are going very fast right now. But that's kind of how the lions behave. Okay, so that's the second class that you're going to define. Then the third class that we require is something called a giant. It's get color, it's always gray, but its Tostring method is the one that changes. So it'll display itself as fee, fi, fo, fum, 6 moves, 6 moves, 6 moves, 6 moves. That's kind of how it behaves. It's get move, it always infects when an enemy's in front, otherwise it hops as possible, and otherwise it turns right. So this is a very similar kind of behavior to what we had with the bears, but the bears turn left and the giants turn right. You can try to figure out what you think, kind of a guess as to how that's going to behave. So let me come down here and get my little paragraph about what's going on with giants. So it says to try running the simulator with 30 giants in the world. So let's comment out the lion and we'll uncomment the giant. So we'll compile and then and then we'll go ahead and run. And let me bring up this, and then we'll kind of watch what's going on with the simulator. So they should all be displayed as fee, so we kind of see them displaying themselves as fee. Now, critters, if they say fee, fi, fo, fum, and you can even use a longer string, it'll make it look like your critter is really big, like it's really wide or something. But it isn't truly. Critters are skinny things as if they're one character. So in terms of the way the simulator keeps track of what's going on in the world, it's not like you're really a bigger critter. It's just that you have the opportunity to display yourself as if you were a wider critter. Makes it a little more interesting, in terms of what you can do with this critter. They should all be displayed as phi. This should be true for steps 0, 1, 2, 3, 4, and 5. So we're on step 0. So if we kind of step forward 1, 2, 3, 4, 5, and it's phi for all of these different things, for 0, 1, 2, 3, 4, 5. When you get to step 6, they should all switch to displaying phi. So I'm going to go ahead and go to step 6. So we see a 6. They all switch to phi, and it should stay that way for steps 6, 7, 8, 9, 10, and 11. So 6, 7, 8, 9, 10, and 11. So that's all of that. Then they should be faux for steps 12 through 17. So boom, they all switch to faux. 12, 13, 14, 15, 16, 17. And then they should switch to fum for steps 18 through 23. So fum for 18 through 23. And then it says, then they should go back to phi for 6 more steps and so on. So that was through 23, so that means that 1 more and they're back to phi. Now, let me mention something about what is involved in doing this homework. So we've mentioned the idea that that objects have state and behavior. And so those are key concepts. And so what I've done here in describing the class is I have described the behavior of each of these different kinds of critters, how a bear is supposed to behave, how a lion is supposed to behave, how a giant is supposed to behave, and I've given you debugging hints about how to verify that it's behaving properly. So you are supposed to write a class that produces that behavior. We do not tell you what state information to have, what fields to have. That's for you to figure out. That's kind of one of the hardest things about this homework, is figuring out, well, in order to have bears behave that way, what kind of state information would each bear have to keep track of? What would it have to be remembering in order to be able to do the thing that it's supposed to do? So that's a lot of what's going on in the homework here, is that for each of these 3 classes, you are figuring out what state information, what fields to include. Sometimes students will post things to the message board. I was going to have the following fields. Is that okay? We won't answer that, and we wouldn't make that public, because then you'd be telling everybody else in the class your solution to the problem. So it's your choice. You're deciding what fields to have. So that's kind of up to you to decide what fields to have for this particular class, for each of the different classes that you're supposed to write, and then for the Husky one that you're going to create. Okay, so those are the 3 required classes. Normally I'd ask for questions, and normally I get a lot of questions. This is going to be a week where it's a very good idea to be going to section, because the TAs are going to be going over this. There's some critter problems there with a solution that'll be available at the end of the day tomorrow. So those will be good things for you to be able to look at. I'm going to take a little time in Friday's lecture, maybe in Monday's lecture as well, to say a little more about critters. So, I assume that it's going to take you guys a while to start reading, and I'd like to point out some things. So anyway, there'll be a little bit of extra information that we give in those. All right, but let me tell you a little bit more. Let's take a look a little bit more about what's going on. So let me go ahead and quit this. Well, let me do this first. Let's just kind of see what happens when I add all of the bears and the lions and the giant. So what if we added them all? And then let's throw in food. So we'll just kind of see what happens when we have a bunch of different critters. I don't know if you have any predictions, but so we'll go ahead and compile and run. So initially it's going to show 30 of each of these kinds of critters. It tries to show you the one that has the highest count. They're all tied, so it just kind of picks the first one that has that count here. But if we go ahead and start, we can watch these different critters wandering around the world. So this is a more interesting kind of critter simulation when there's a lot of different kinds of critters. Bears are doing very well. I think it's kind of just a a fluke of the particular combination of critters that we throw in here that bear tends to win. It's not because bear is a particularly smart strategy. None of these strategies are very smart strategies in terms of trying to win. I focused more on how they display themselves because I wanted to make it easy for you to be able to verify that you had it right, that your critters were behaving properly. And so observing their behavior, the string and the color, that's a lot easier to do. Oh, bears have won. So we've got 120 bears. The world has been taken over completely by bears. And I think that's what you're going to find happens when you have this particular combination of critters. So again, none of these critters we're having you write are very good critters. They're not a good model to follow if you're trying to create a critter that's going to win in terms of surviving relative to other critters. Let me mention something also that's useful to understand about this homework. So I know that some of you are going to want to do, you're busy or there's a lot going on this quarter. You're not going to want to spend a huge amount of time on the homework. So for those students, I've made sure that you don't have to do a whole lot. So you're not going to have to understand everything about this critter simulation. But there's kind of at the other end, some of you who have more time and have more interest and might want to spend a little bit more time. I wanted to make this rich enough that there was an opportunity to do some interesting things. So there's a lot of extra stuff that's part of this homework that is not part of the minimal requirements. So it's not something that you have to understand in order to get full credit, for homework 8. So I've tried to accommodate people who don't want to spend a whole lot of time, but also accommodate those who get interested and want to spend more time. All right, but we kind of did see these are all kind of crappy strategies in terms of trying to survive: the bear, the lion, and the giant. I wanted to show you the critter class. So there's a basic class known as critter, and it's got a lot of stuff in it. So it has things that are known as enums, enumerated types. And don't worry about the syntax. You don't have to worry about what all of this means. But here's where that hop and left and right and infect are, all part of an enumerated type known as action. Now, all of these different things are described in the assignment write-up. So there are tables of these early in the assignment write-up. So action.hop, action.left, action.right, action.infect. So kind of those different things are all mentioned here in the assignment write-up. So the critter class is there. You don't have to, in general, understand a lot about the critter class, but you do have to understand a few things. So let me mention there are two important things to understand about the critter class. So one of them, it's mentioned here, well, it's showing you the food class here. I'll bring it up in JGraphs, but I think it's a little... we get the color coding and everything as well when we do that. So let me bring it up in the context of the food class. So this is the definition for the class known as food. Now, one of the things you need to know about the critter class is that you're going to include this little notation in the header of the class, extends critter. That is connecting this class to the critter class through something that's known as inheritance. Friday's lecture is about inheritance, so I'm going to say a lot more about this in Friday's lecture. You don't have to understand a lot about it other than to kind of know that you need that phrase, that all of your critter classes are going to say extends critter. And the idea is that by doing this, it gives you access to things that are defined here inside of the critter class. So in particular, for example, there is action.infect is something that's defined in the critter class, but by saying extends critter up here, we have access to it. So you can refer to all of these different things that are in the tables, all the different actions and so forth, different directions. There's a bunch of these that are included in enumerated types here in the critter class, and those become available to you when you say extends critter. So those are the two things to know. Include the extends critter in the header, know that gives you access. Now, food is purposely a really simple class. It always returns a green F, so it's always displayed as green and S and F. What I had in mind was something that's easy to pick off, something, well, that's why it's called food, so that other critters can feed on it, can kind of convert it. And so, it does infect. It's just kind of sitting there trying to infect. And if something wanders in front of it, it might get lucky and infect that thing and turn it into food as well. But that doesn't happen very often. So more often the critters, the food objects are just sitting there and something comes along and kind of turns it into their kind of critter. So food tends to disappear fairly quickly. But this is nice to study because it gives you a good example of a complete critter class. So remember I said 3 methods. You're going to define getMove, you're going to define getColor, you're going to define toString. So this is a very simple one that has all 3 of them defined. Now, they aren't very complicated. Each one just has a simple return. It always behaves exactly the same way, all 3 of these methods, and you're going to do something more intricate. So there's a little bit more. There's a critter info class that I mentioned. There's kind of a description of it here, but I think I want to show it to you in the assignment write-up because I think that this is a nicer way of seeing the critter info information. There's a little table here about the things that you can ask of a critter info object. So remember what I told you is that when I ask your critters to tell me what move they want to do, I'll give them a critter info object that they can ask questions of. So you can ask this critter info object, hey, what's in front of me? What kind of thing is in front of me, so that it can see things like, is there a wall in front of me? Is there an empty space in front of me? Is there something of my species in front of me? Or is there something of another species in front of me? So that's a question you can ask of the critter info object. You can ask it what's in front of you. You can also ask what's behind you, what's to your left, and what's to your right. What direction are you facing? So there's a bunch of different questions you can ask of the critter info. Now, remember I said that the minimal assignment doesn't require all that much. The minimal assignment would require you to use getFront, getLeft, and getRight. So those are the 3 that you'll use in defining the 3 required classes that we've defined for you. You only need to be looking at the front, the left, and the right. You don't need to be looking behind you, and you don't need to be seeing what direction you're facing, these other things. Those are for the Husky class, for you doing your own more creative kind of thing. Like if you wanted all of your critters to face north, you can ask what direction they're facing so that you can do something with that. But that's not part of the assignment. That's not part of the 3 required classes. So the only things you need from critter info for the required classes are getFront, getLeft, and getRight. So again, you get to kind of ask this critter info object about various kinds of things so that you can make decisions. Well, let me show you an example of that. So there's a flytrap class. Now, food was amazingly simple, right? It had the 3 methods, but they always returned exactly the same thing. Flytrap is a very interesting strategy. It's a very simple strategy, but it turns out that it does quite well. So it returns a red T. So getColor and toString are always returning a red T for the flytrap, but getMove is a little bit more complicated. I'm talking to that critter info object. I say to the critter info object, tell me what's in front of me. And you use an equals equals here when you're comparing it against this constant, neighbor.other. Remember I showed you in that there were the table of the different kinds of neighbors. So neighbor.other, neighbor.same, empty wall. So this is an example of a test where you can see whether what's in front of me is some other kind of critter than I want to do action.infect. And otherwise what it does is it turns left. So that's the flytrap strategy. It's very simple. If there's a critter in front of it that's not a flytrap, it's of an other kind, it infects. So it infects, an enemy if there's one in front of it, and otherwise it always turns left. So they're kind of sitting and spinning until something wanders around it, and then it infects it. So that's kind of what a flytrap does. It never does hop. It never does a move. So you're going to be writing code like this. You're going to be writing if-elses where you'll be saying, depending upon what's going on, what I see going on in the world, I'm going to take different kinds of actions. Now, what I would recommend is that this flytrap class is included in assignment8.zip. It's on the class webpage. This is provided to you. When I went to go and define a critter class, I'd begin with flytrap. I'd open up flytrap and I'd change the name of the class to whatever class I was trying to define, and then I would redefine what's inside. I would kind of, give it different behavior. That way, you automatically start with a critter that compiles and does something, it does the flytrap type behavior, but then you just kind of turn it into something that does the other kind of behavior. So it's very helpful to have a starting point, and flytrap turns out to be a great starting point. So let me throw in flytraps. So let's see what happens. It's a little bit, unpredictable. Basically, with all of these different critters wandering around, sometimes flytraps get wiped out early. So that, that's basically the only hope of the world, is if flytraps get eliminated early. But so maybe you could kind of watch what's going on with the flytraps. We're down to 20, 15. There's a little flytrap colony there. There's 9, 11, 10 flytraps left. Maybe we'll speed it up a little bit. Flytraps, there's 11. This one's interesting where giants did well this time round. So we've got, and it wiped out the flytraps. So flytraps disappeared. So that was an interesting outcome. That doesn't happen very often, but it's random, so we can see different kind of outcomes on different runs. Let's let this one run for a while. And flytraps, they're not getting wiped out. Flytraps, you can kind of see that there's a concentration. There's a little flytrap colony right here, and a little flytrap colony right here. It's the red T's. And we've got 60, 70 flytraps and giants. So they're kind of in parity here, but flytraps are starting to do a little bit better. We could watch it go over time. Flytraps tend to win, It's kind of annoying that is so, especially since it's such a simple strategy that flytraps tend to do fairly well. Let me slow this one back down again. Let me show you, and let me stop the simulation. There was another feature of the simulator that I wanted to point out to you that you understand. So you need to sometimes know which direction critters are facing. And so there's an option here where you can ask for debug. And debug gives you little arrows kind of pointing in the direction. So you can see these giants, are kind of all facing this way. These are all facing this way, and facing this way. So I can go ahead and start the simulation running, and I can see which direction things are facing. So this can be very helpful too when you're debugging, to make sure that things are making, that your critters are making the right decisions. So this is a very useful option to be able to do the debug option, and you can just click again to turn it back off again. So you can turn it on with the debug option, and you can turn it back off again. Maybe I'll come back one more time. Let's try running it. And what you'll notice about the flytraps is you'll see that spinning action of the flytraps. So maybe we'll do the debug here. And it's kind of interesting now. We're not seeing the normal to strings. We're seeing kind of the different directions. Oh, flytraps got wiped out. And giants. Interesting. Okay. Let's try again. Let's see if we can have one where the flytraps win again. So we'll let it run, and we'll put it into debug mode. And you can see kind of there's some flytraps in the middle here, like this one right here, where they're spinning around, spinning, waiting for something to come near them that they can infect. And so giants are doing better for now, but I'll bet you over time flytraps are going to do better. There is an option here where you can click ahead 100 steps at a time. So if you want to kind of go fast forward into the future, you can do that. Look, they're almost tied again, and I'll bet you that what's going to happen over time is that these flytraps are going to win. So it's just a matter of time, that we watch to see flytraps take over the world. So part of your Husky assignment, if you want to compete in the tournament, is trying to come up with a better flytrap. That's trying to come up with a strategy that does better than what flytrap does. All right, well, that's what I was going to describe about the homework today. As I said, I'm going to say more about it in Friday's lecture and probably in Monday's lecture as well. But we can go ahead and end it there for today.